The last situation I want to look at that involves exponential functions is cooling and warming. It turns out if you put an object in a large environment, then it will cool up or cool down or warm up, depending on whether it's cooler or warmer than its environment, so that the difference between its temperature and the temperature of the environment decays exponentially. What I mean by a large environment is an environment that's large enough that when the object cools down, the environment doesn't warm up appreciably in response. So, if you put a really warm mug in a very large room, the large room isn't going to warm up much as the mug cools down because the large room is just too big. So that's what I mean by large. So for example, suppose that a lump of metal starts at 200 degrees Celsius in a 20-degree room. If the metal cools down to 190 degrees in 1 minute, how long will it be until the metal cools to 50 degrees? Maybe we want to wait until it's 50 degrees so that we can pick it up and not burn ourselves. So the difference between the temperature of the object and the temperature of the environment is what decays exponentially. So when we write our exponential decay, so a to the kt, this doesn't give us the temperature of the object. This gives us the difference of the temperature of the object and the temperature of the environment, right? So we have to be careful here. The temperature of the environment we're assuming is constant because the environment is large, so the temperature of the environment isn't going to change appreciably as the object cools down or warms up, cools down in this case. So we can move this temperature of the environment to the other side. We get that the temperature of the object as a function of time is a to the kt minus the temperature, plus the temperature of the environment. Okay, now the temperature of the environment, we know it's 20 degrees, so we can put that in here. And we have some data points. We know that the metal starts at 200 degrees, so if we plug in time 0, I'm going to stop writing this little O here. So let's stop writing that. So that at time 0, the temperature of the metal is 200. But if we plug 0 into this formula, we get AE to the 0 plus 20. So we get 200 equals A plus 20. And that means A is 180. Notice that in this cooling situation, A is not the initial temperature, right? Because of this extra shift happening over here. So A is the initial difference in temperature. Okay, so A is 180. We have another data point. The temperature is 190 after 1 minute. So that means 190 is the temperature at time 1. Now we can use our formula to evaluate capital T of 1. So that's A, which is 180, times e to the k times time, which is 1 minute, plus 20. Now we can solve this for k. So subtract 20 from both sides. 170 equals 180 e to the k, and then divide 17 over 18 equals e to the k, and then take natural logs. So k is natural log 17 over 18, and that is about, looks like negative 0.05716. Again, this is negative because we have exponential decay, right? The temperature of the object is decaying towards the temperature of the environment and not exponentially growing away from the temperature of the environment. All right, so now that we know k, we know our temperature function. So temperature at time t, t minutes, is 180 times e to the minus 0.05716 t plus 20. Now we wanted to know when the temperature got down to 50, so now we can just set this equal to 50 degrees. So 50 equals 180 times e to the negative 0.05716 t plus 20. So subtract 20 from both sides. That's going to give us a 30 over here. Then divide both sides by 180. 30 over 180 is 1 over 6, I think, right? Yeah. Equals e to the negative 0.05716 t. Then take natural log on both sides. So natural log of 1 over 6 is negative 0.05716 t. And then divide. T is natural log of 1 over 6 over negative 0.05716. And then punch this all into a calculator. Natural log 1 over 6 divided by negative 0.05716, 31.35. So, and this is in minutes, remember. So we're going to have to wait a little over half an hour for this lump of metal to be cool enough to handle.